this lecture, we will discuss about two shift registers, that is serial in, parallel out shift register, parallel in, parallel out shift register. In the previous lecture, we have discussed about serial in, serial out shift register. In that, we have seen how to perform right shift and how to perform left shift also. Right? Now, first we will see serial in, parallel out shift register. So this is the logic diagram of 4-bit serial in, parallel out shift register. So the moment we set 4-bit, so we have to use 4 flip-flops, and here I am using D flip-flops. We can use JK flip-flop or SR flip-flop also. And here the clock is applied simultaneously for all the flip-flops, and this clock is negative edge trigger clock because there is a bubble. We can use positive edge trigger clock also. And I am applying the input at the first flip-flop. So generally the first flip-flop always give the MSB, that is most significant bit, and the last flip-flop will give LSB, that is least significant bit. Right? So data will be applied at the first flip-flop 1 bit at a time, that will be shifted towards the last flip-flop. Right? And the moment the data is stored, so the data will be taken out parallelly. So that also we will see how. Now we will see the operation, how it is performing the serial in, parallel out using this table. Right? So here I mentioned clock, then data in, and these are the 4 outputs Q3, Q2, Q1, Q0. So initially we will assume that all are 0, or we can say all are in clear mode. Right? Suppose if I want to store 1, 0, 1, 1. Right? So in this, the last bit is called least significant bit, the first bit is called most significant bit. So now which bit we need to apply? See, Q3 is MSB, so we have to apply first LSB and we have to shift towards right, then it will be stored 1011 after some time. Right? Now first we have to apply the 1, that is the least significant bit, then we have to apply clock, which is showing the negative edge trigger, that's why the arrow is downward. Now if I see the diagram, what we'll see? So all are 0 initially. Now we have to apply data at the first flip-flop. Now if I apply 1 here and if I apply the clock, see, clock is applied simultaneously. So whatever the data available at all the flip-flop inputs, that will be transferred to the output. See, that is operation of D flip-flop, right? So whatever we apply, that if I apply 0 and clock applied, that 0 will be transferred to the output. If I apply 1 and one more clock, then it will be transferred to the output. Right? So here D3 is 1, D2 is 0 because we assume that initially it is 0. Similarly D1 is 0, D0 is also 0. So what will happen the moment we apply clock? So this 1 will be transferred here. So we'll write here. Then this 0 will be transferred here, then this 0 will be transferred here, and this 0 will be transferred here. So sometimes we may get doubt that, so this 1 will be transferred here. No, we are applying the same clock, so whatever the available at that moment, that only will be transferred. See, when we apply 1 and we apply the clock, so D2 input is 0, D1 input is 0, D0 input is 0. Right? The moment we apply the clock, this 1 is transferred here, this 0 will be transferred here, this 0 will be transferred here, and so on. Right? So don't take this one as the input of this D2 flip-flop. So that will be happen next clock edge. Right? So that is after first clock edge. So the state of the register is 1 0 0 0. So what will happen? So this 1 will be transferred to the Q3, this Q3 here, Q1 here, Q here. Right? So this is what is happening, right shift is happening. Next, what we need to apply? Next again one more 1. Now what will happen? So this will be transferred here, so that also we'll see using the diagram only, logic diagram. Now again I am applying 1. So if I apply the clock, what will happen? And see, I applied 1 here, but what is the input of the flip-flop? See, D2 means now it is changed 0 to 1. Then again this D1 0 to 0, 0 to 0. So the moment we apply the clock, this 1 will be transferred here, this 1 will be transferred here, this 0 will be transferred here, this 0 will be transferred here. So same thing we can have here. This 1 will be transferred here, this 1 here, this 0 here. Now the present state is 1 1 0 0. Next, which bit we have to apply? This 0. So 0 means again same operation. 0 will be transferred here, 1 will be transferred here, and 0. The last bit we have to apply 1. So what will happen? 1 0 1 1. That is, after 4 clock pulses we have stored our data 1011, right? And this 1011 is available after 4 clock pulses. So here we can apply 0 here, so that 0 will be transferred here, 1 will be transferred here, 1 will be transferred, and 0 will be transferred. Then last bit, so 1 if I apply, that 1 will be transferred here, 0 will be transferred here, 1 and 1. See, this is the required information. So what is this? 1011. So the moment the Q3 output is 1, so we can take it out. Similarly, this is 0, this is 1 and 1. See, parallelly we are taking the out. So after 4 clock pulses the data is available, so we can take any time we want, right? So in the serial in serial out shift register, so we need extra clock pulses to take it out the data, but in this register after 4th clock the data is available, so we can take any time we want. So that is an important point, that is, after 4 clock pulses the data is available, right? So we can take at any time we want. But how many clock pulses required to store the data in this serial in parallel out shift register? So 4 clock pulses required, right? After that we can take at any time. Now we'll see what is the application of the serial in parallel out shift register. Now first we'll draw the symbol. So shift register 4, here I'll apply the data in and with the negative edge triggered clock, and the data is available parallel, right? Something like this, 4 bit, right? So 4 outputs are there, so this is parallel out. Now what is happening actually here is, see, so we inserted 1011 but 1 bit at a time, so serially the data is coming and we are taking out parallel. So what is happening here is serial to parallel conversion of data. Yes or no? So this is the most important application, that is, this shift registers can perform serial to parallel conversion of this data. Now where we require this conversions are, suppose if you see the telephone modem, so there is a wire, generally we say channel, and in this telephone modem, or we can say the computer, so here we'll have modem, right? Modem. So here we can use the computer. So computer generally will generate the parallel data, right? Now but this channel will allow the data go serially, right? So what we need there, we need conversions. So here data is coming serially, so 101010 and so on, right? So 1 bit at a time, so it is coming serially. Suppose I need up to 8 bits, so 4 4, so 8 bit I need to perform some task, or it is denoting as some logic or some operation. So this is serial is coming, so 8 bit of data packets, so there should be some device to convert this 8 bit data which is coming serially to convert into parallel, right? So this 0 1 0 0 1 0 1 1. So here I need to use serial in parallel out shift register to convert this 8 bit data into like this. So then this indicates some, suppose capital A, some alphabet A, right, or some alphabet B or some other thing, right? So we need some conversions there in this modems to convert the serial data to parallel. Similarly, if computer is generating parallel data but this channel will allow only serial data, so what we need here, we need opposite conversion, that is parallel in serial out shift register. So parallel in serial out, so serially the data will go to this through this channel or through this wire, right? So that is where we will use this serial in parallel out shift registers or parallel in serial out shift registers, right? So here telephone modems we will use these shift registers, right? Remember this point. So when we discuss this parallel serial out shift register, the application of that parallel in serial out shift registers also will be used in telephone modems, okay, right? Next we'll discuss about the parallel in parallel out shift registers, right? So this is the logic diagram of parallel in parallel out shift register. Again 4-bit only, so 4 flip-flops we are using, and the same clock applied to all the flip-flops. Here I am using positive edge triggered flip-flop. Previously I have used negative edge triggered clock. Now if I see again, the first flip-flop will give the MSB, the last flip-flop will give LSB, right? Now so the data is available at a time at the all the flip-flops. Now the moment we apply the clock, that will be transferred to the output, then we can take any time we want. So it's very simple. So actually there is no shifting operation, yes or no? So the moment we apply the input, that will be transferred to the output for one clock. So it is nothing but a normal register, yes or no? There is no shifting actually. So this is called a normal register, or we can say storage register, or we can say buffer register. So what is happening here is, the moment we apply the clock, the data is available at the input of the register, transferred to the output. So simply it is simple normal register. So what we discussed in the previous lectures, so that is simple register, right? Or we can say the other names, storage register or buffer register. Now so what is the operation? Suppose if I want to store 1 1 0 0, so we have applied the input as 1 1 0 0. The moment we apply the clock, which is a positive edge triggered, so what will happen? This will be transferred here. So Q3 will be 1, Q2 will be 1, Q1 will be 1, 0, Q0 will be 0. So 1 1 0 0. The moment we apply one clock, the data will be transferred to the output. So we can have like this: the clock I3, I2, I1, I0. This is the data, and this is outputs Q3, Q2, Q1, Q0. So initially suppose all are 0. So this is initially. So the moment we apply one clock, which is positive edge triggered, and I applied the 1 1 0 0. So what will happen? Directly it will be transferred to output, right? So here parallel in parallel out shift registers, one clock pulse is enough to store the data, right? And we can take any time we want. So after one clock pulse, the data is available for either storage, or we can say, or to take it out also. So because there is no shifting operation, so that's why this register is also called normal register or storage register or buffer register, right? So same thing, this parallel in parallel out shift register, or this serial in parallel out shift register operations can be explained using the timing diagram also. So nothing is there, so that's why I'm not drawing the timing diagrams, because so clock applied, whatever the data is available, that will be transferred. So nothing is there, right? So that you can do on your own. You can draw the timing diagram also, right? Now what is the application of this parallel in parallel out shift register? Simple, for storaging it. So general purpose registers are there, no? So there we will use this parallel in parallel out shift registers, or we can say simple register. It's not any shifting is not happening in this register, right? In the next lecture we'll see parallel in serial out shift register.